everybody. My name's Dr. Benjamin Jones. I'm Assistant Professor here at the University of Nottingham. Welcome to this webinar. It's brought to you by the CIBSE Natural Ventilation Group and its partners Vertical and the Air Infiltration and Ventilation Centre. The Natural Ventilation Group is an international group comprising around 30 committee members who are from both industry and academia. We have a wider membership of over 10,000. Our aims of our group are to ensure that natural ventilation is to be properly considered at the design stage in compete with mechanical ventilation and air conditioning, and to disseminate knowledge via webinars and seminars like this. I'd like to introduce you to my co-host today, who is Professor Sean Fitzgerald. He's a co-founder of Breathing Buildings. He holds a PhD from Cambridge University and has conducted research into natural ventilation and energy demand reduction. Sean is a Fellow of the Royal Academy of Engineering and a Royal Academy of Engineering Visiting Professor at the University of Cambridge. Sean, over to you.
Good afternoon, everybody. So the purpose of this webinar was as a result of various discussions in the industry regarding the types of tests that are undertaken by various companies who are trying to ensure that whatever they're selling, and indeed what designers are designing too, are known. What has become extremely clear is that there seems to be quite a lot of discrepancy between what people mean by certain tests. And therefore the purpose of this webinar is to help you understand what different people mean by tests in various areas. So the biggest issues that we've got regarding tests in buildings, we're going to cover very briefly why are we bothering testing things, what to test, and then I'm going to hand over to my esteemed colleagues to then expand on where, when, and how to interpret the test results. So why test? Well, in the world of natural ventilation, we have buildings that we're trying to create that are using less fan power than other building types. But whether we are able to achieve a building that's satisfactory and how that's going to work in reality, there are lots of things that are at stake. The first thing is actually air quality. So we are worried about whether we're going to be creating an environment that is the right type of air quality for the occupants. And that itself is a function not only of pollutants released in the space, but is of course also a function of the quality of the outside air. In association with air quality, the air is often used in many building types to regulate the temperature in a building. So if it's warmer outside, we might want to bring more of that air in to help provide a cooling facility. And some naturally ventilated buildings in the past have been prone to overheating. Conversely, if it's chilly outside, then some naturally ventilated buildings, in history at least, have been prone to either cold draft or just not being adequately heated. Now, whether you have a naturally ventilated building, and it may have some assistance with some mechanical ventilation, or it could just be near a busy road, you then have issues to do with how noisy it is in the space. And that noise is something that's important regarding not only in terms of the noise generated by any equipment that you may have, but also, of course, the noise linking one room to another, and as well as from the outside to the inside. Natural ventilation does require larger openings, and larger openings therefore need weathering. And the primary function of weathering of naturally ventilated buildings is to try and ensure that you are limiting the ingress of water and snow into that building. And how that is assessed and how that you gauge one product versus another, or what design standards you're working to, is extremely important. Penultimately, naturally ventilated buildings have historically been extremely well encouraged as a result of their intention, at least, to have a lower energy use and therefore lower carbon footprint. And therefore, any equipment that you use needs to be well categorized in terms of how much energy it is going to be using. Finally, the building, ultimately, it all comes down to money, and therefore how much money you spend on a given product, or how much a contractor spends on a given product, will determine the success of that building in terms of whether it's going to get built, and therefore how much ventilation area, how much air you're going to get. It all comes down to money, which of course the suppliers are going to be extremely keen for you to understand what you get for your money. So what is it that is actually tested? The testing that we're actually going to do and discuss is as follows. We're going to cover these various topics: water leakage rates, the resistance to airflow, air leakage, actually the conductive losses through dampers and things like that. The flow rates into and out of space, which are regulating air quality and indeed temperatures. We're going to cover that regarding the the world of mechanical ventilation suppliers and their expertise in this area, and then comparing that with the natural ventilation equipment that is used to try and achieve the same objectives. And then finally, we're going to be looking at energy use, noise attenuation, noise generation. And I'm going to now hand over to our esteemed colleagues. The people that are going to be working with us through these topics this afternoon are the following. We're going to be having Mark Roper from BSRIA talking about weather testing. We're going to be having a presentation from Jerry CIBSE, who works for Price Industries in the United States. So not only does Jerry have expertise in mechanical ventilation, but he's going to be able to help provide a lens regarding how they think about these sorts of topics in overseas markets. David Clark from SRL and Roy Jones from Gilbert. Over to you.
You're quite fortunate in that you are able to ask these panelists questions, and you can do this by looking at your GoToWebinar panel, and you should be able to see something which says questions. Feel free to send them to me and to Sean so that we can see them, and if we have time then we'll post them to the speakers. We hope to summarise at the end with any questions to the speakers directly. So our first speaker today is Mark Roper from BSRIA. He's a principal test engineer with them. He's been working there for the last 20 years. He's currently responsible for the management of various areas of testing, including products such as stoves, high temperature fans, flues and chimneys. He has direct experience testing weather louvers and other related products for a wide range of UK and international clients.
Thank you, Ben. Thank you, Sean. Good afternoon, everyone. Yes, I hope to spend a few minutes explaining what we mean by weather louver testing, and hopefully this will better inform future design decisions when you can assess how relevant these results are and whether you need to apply some further interpretation to them. Okay. Sorry, Ben, do I have control of the presentation yet?
Yes, you do. If you're struggling, just shout next slide and I'll scroll for you. How about that?
Okay, there we go. Thank you. Yeah, so the test standards, its full formal title is Ventilation for Buildings, Terminals, Performance Testing of Louvers Subject to Simulated Rain, which is far too long for most people, so we usually simply refer to 13030. It covers particularly performance in two categories, which is the weather performance, and it also looks at the aerodynamic performance of a weather louver. It's based on testing a standardized sample, so as close as possible. The idea is that all the samples we test will be as close as possible to 1,000 millimeters by 1,000 millimeters, or the nearest hole blade below that. And the aim is to try and provide a common basis for comparison. So it's accepted that we can't cover every single weather condition, but it provides a single fairly severe set of weather conditions that allows a comparison of products on a common basis. And the rain test principles are that you'll have fixed external conditions. So there is always during the testing a 13 meters a second, about 30-mile-an-hour wind onto the face of the louver, and a fixed water spray, which is adjusted so that we achieve 75 litres an hour through a 1,000 millimeter by 1,000 millimeter calibration plate. So basically we have a 1 meter by 1 meter hole in the wall, and we set up the water spray so that we will get 75 litres an hour through that hole. And then those fixed external conditions carry on throughout the test, and then we subject the louver to a range of different airflows from 0 to 3.5 meters per second face velocities, up in 0.5 meter per second increments, and we hold each velocity for at least 30 minutes. So there are 8 settings, at least 30 minutes with settling time. So a full weather performance test can take half a day to a day. So it's not the world's most exciting test to watch, but it does get us some results on that. Next slide, please. So a quick look at just a schematic of what we're talking about when we talk about our weather louver test facility. Airflow on this slide is from left to right. So on the left we have our wind simulation equipment, basically a very large fan, blows towards the weather section. There's a set of spray nozzles in front of the fan so that the rain is introduced into the airstream. It blows against our test louver, which is in the center, and then the water eliminator section captures any water that passes through. And then beyond this, further to the right, there's a set of airflow measurement systems so that we can monitor the airflow being drawn through the louver. So, a quick picture of the BSRIA test facility, taken some years ago, but one of the clearest shots we have, so you can see the whole thing in one go. So the fan is there on the left, blowing towards the weather section. In the center you can see a blue square, which is the louver under test, and then on behind that the water collection and the aerodynamic testing section. Okay, so we have a quick video. I hope it's come out. It's not the best quality video in the world, but showing a test actually in progress. So we had a shot at the beginning there of the water nozzles firing water into the airstream. We've turned the sound down so you don't get the wind noise, so you can actually hear me speak to you. And you can see there is water pooling on the louver and starting to trickle down it there. So that's the external conditions. So it's always a very bad day in the weather section. And then for the rain penetration, so this is the other side of the louver. So you can see there the water droplets falling off the blades and being drawn through to the water collection section, and they will be collected there and effectively drained into a bucket, which we will weigh to see how much water comes out the far side. Okay. This is a typical set of test results. So on our table on the left, first of all we're looking at the airflow, a different set of airflow rates, and we're working up through our face velocity from 0 to 3.5 meters per second in 0.5 meter per second increments. Down the center of that table there are some figures for the water results. We've got a figure there for supply of 93 litres per hour. Now I mentioned earlier that we are looking for 75 litres an hour to go through a 1 meter square hole. So to achieve that we actually supply more water because there's overspray and splashback. So we've worked out that 93 litres an hour is the amount of water to deliver that would give us 75 litres an hour through a 1 meter opening. And then the penetrated figure is the amount of water that's actually gone through and been collected and measured. So we have a figure there in litres per hour. And from this we can work out the effectiveness. So that percentage figure towards the right of the table is the proportion of water that's been rejected. So for our first reading there we're 99.5% effective. So only 0.5% of the water that would otherwise have gone through our hole in the wall has made it through and has been collected, and the rest has been rejected by the louver. Perhaps as you'd expect, as the velocity, air velocity through the louver increases, the effectiveness falls away till at the end we're only 42% effective. And there are a series of classes in the louver, and that's the final column on the right of that table, and that goes from class A, and this particular louver passes through all three classes A, B, C and D. And much of this is then shown on the graph on the right, which is also typically in a test report. I talked about the classes for the rain classification. They do A, B, C and D. The numbers are given there. Perhaps one of the interesting things to note is that class A, even a class A louver, if it's 99% effective, you can still have up to 0.75 litres an hour, or probably about a bottle of Coke's worth, through the louver during that hour. So you have to assess just how effective you need your louver to be and what exactly is behind it to try and rate what sort of level of performance you need. And so we have the 4 classes there, and basically anything below 80% effective is seen as a class D. Right, so that was the range side of it. Looking very quickly at the airflow side, on this sort of test, the louver gets mounted in a test plenum, air is drawn through the louver, and we measure the pressure drop for different volumes. So there's no external wind pressure on this test, it's purely air drawn through the louver. The standard says the lowest flow should be when you have a pressure drop greater than 10 pascals, and suggests the highest flow for the testing should be greater than 3.5 meters per second. And from these values you can both graph the results, which we'll have a look at shortly, and it also allows the calculation of the coefficient of discharge or the coefficient of entry. The difference between those two is simply the direction of airflow through the louver. So if it's a coefficient of entry, it's an intake louver. If it's coefficient of discharge, it's discharging air from the building. Now, I know coefficient of discharge is defined in various ways for various different applications. So this is what we mean for 13030 testing. It's defined first of all as the actual airflow through the louver divided by the theoretical airflow, which is not terribly informative. So the theoretical airflow is then given by the equation in the center there. This is where I hope I've rearranged from the standard correctly. I'm sure someone will point it out if I haven't. But what it's trying to do is work out what, for a particular pressure drop, what flow rate would you get through a perfect orifice plate the same size as the louver. So there is a notional perfect louver with no air drop due to blades or any other obstruction, simply through the edge effects, and it uses this as a benchmark against which to rate the louver and to come up with a figure. So the closer your CD or CE gets to 1, the less resistive the louver is. It is also size sensitive, so if your sample gets significantly smaller than 1 meter by 1 meter, you find the CD goes up, and this is because the ratio of the edges to the center area, which is giving your resistance, changes. So ideally we aim to test a sample as close to 1000 millimeters by 1000 millimeters as possible, so that we're comparing on a common basis. And this is an example set of airflow test results. Tabulate on the left, graphical representation on the right. And on the left of the table, we can see that there's a set of louver pressure drops versus a face velocity. You can see in there we've also calculated those theoretical airflows, which are significantly higher. And finally, on the right-hand side, we've calculated the coefficient. So this particular unit has a coefficient of 0.193, which makes it, in the grading system, which we'll have a look at on the next slide, a class 4. So you can see there are 4 classes, 1, 2, 3, and 4. So the best is class 1. And you can see that stretches all the way from 0.4 to 1. And one of the reasons that's such a broad class is actually you're probably unlikely to see figures very much above 0.4 for a louver that's actually doing much in the way of screening. So class 1 louvers are relatively rare, because if anyone ever tells you they have a louver with a CD of 1, then they've created a perfect louver with no resistance at all, or they've just provided you with a hole in the wall. So typically 0.4 is some of the least resistive, and then we work through the various classes down there so that they can be graded, and you can have an indicative number for how much air resistance your louver has. So that's a very quick look at weather louver testing. I hope it's all made sense. What does that mean in real life? Well, the first thing is it's not real life. It is intended to be a comparative benchmark, so it will let you compare products, and it's good for comparing them. I use the simile here of light car mileage figures, which are good for comparisons, although in the wake of VW and other revelations, perhaps that's not a good comparison to use anymore. It is only one weather condition. It's a fairly obnoxious weather condition. I can't think there are many places in the UK which regularly see 75 millimeters of rain an hour coming in horizontally, but obviously it's not impossible. And it's severe so that we can differentiate sensibly between louvers. It's only on a smaller sample. There can be some issues with airflow in that the framing effects can affect the results. And if you're, one of the things we find with louvers is that one of the, some louvers work very well until they reach a certain rate, and then you have to look at how well they're actually training the louver. So the louver blades have worked successfully, but you then have to remove the rainfall products. And finally, the one thing no lab test can tell you is how well it will be installed and how good the product is you've got on site. So obviously we can only tell you so much. Thank you very much. I hope that's been of help.
Thank you very much, Mark. I'm going to move swiftly on to Jerry. It would be great if all 282 out there listening to us now, if you could ask questions as and when you think of them, so that we can log them and ask them at the end. I'd like to introduce you now to Jerry CIBSE. Jerry has a PhD in mechanical engineering and is the Vice President of Engineering at Price Industries. He has 20 years of experience in the HVAC industry and sits at national level with ASHRAE and the Air Conditioning, Heating and Refrigeration Institute. Jerry is an ASHRAE Distinguished Lecturer and a certified provider of the American Institute of Architects and other professional development house. Jerry.
Thank you. So, when I was asked to talk about this, you know, there's so many different aspects for testing. I'm wondering, do I have mouse control yet? Yes, there we go. So in the United States, we test for various aspects of the design process, including velocity, sound, throw, draft estimation, and also for unusual applications such as the hybrids of radiant cooling combined with stratified systems such as displacement or natural ventilation. So I'm going to talk briefly about some of the tests that we can do. And the whole goal, of course, is an improved indoor environment. And then I'm going to give you several examples of our performance testing in mock-up. Now, at Price Industries, just so you understand a little bit about our capabilities, we do have 3 structures where we do a large amount of education for our design community. We have a full research center in Winnipeg, Manitoba, our corporate headquarters. We have technical centers in Arizona and Atlanta, and then also a mock-up structure in Atlanta. By the way, every time you guys touch your mouse, it takes control away from me, just as a heads up. So, in our structure in Winnipeg, you can see 110 to 115 different types of tests run every day. A large number of them are related to acoustics. Acoustics in the indoor environment, I think, is a fair statement that it's the least understood aspect of most HVAC designers, at least in the States. And it's usually the one that generates the first phone call of complaint. So we have 2 test structures for that. We have a reverberant room that's sized to be able to do the average terminal units and diffusers, grills, registers. And then we have one that can do air handlers up to 60,000 CFM. In terms of mock-ups, we have 3 mock-up rooms in the Winnipeg structure, one with a hot or cold wall. Now, if any of you have ever been to Winnipeg, Manitoba, you may realize that it can get really, really cold, minus 40 to minus 50 C. It's usually the extreme, and I find it amusing that we can't actually simulate it quite that cold. We can only go to minus 40 inside this mock-up, and surprisingly enough, it's a large number of times we have to use that to look at glazing systems in conjunction with the air distribution. It both impact thermal comfort. If we're not concerned about the acoustical aspect, we do throw performance mocking in this throw room or in the Atlanta structure, where we can simulate different heat sources and diffuser sets and so forth. Now, we have a large amount of training, particularly in healthcare in the United States, where we have a large amount of work being done, so we can demonstrate various operating room air distribution systems, or we can actually test them to European or US standards. So if a hospital room has a hybrid construction, say lots of monitors and such, we can actually mock that up. And then we come to the strategic mock-up room, where we can actually test naturally ventilated products in, and I'll talk about that briefly. In Atlanta, I have full-scale mock-ups because of the quantity that we do a year. We have just set them up standard, so I can do classroom, patient room, surgical space, then Cherry Hood ward, do full training. We also can do acoustical testing, where we put a terminal unit over a defined space in a ceiling cavity and measure the actual acoustical sound. This is a check against the standards for estimating sound. In terms of performance testing, this just throws 3 different categories of diffusers and shows the discharge air patterns from them. A perforated product with a discharge velocity pattern is shown below. Very consistent, but it's very loose to the ceiling. It'll come off first compared to the other 3, and usually ends up hitting an occupant in the head, which is usually not a good thing. Then we get into the mid-range product, which is very well defined but has very long throws. Usually you run into problems with this one when you have numerous diffusers in the ceiling. They collide and come off the ceiling, hit an occupant in the head. And then we have the type that's more of an omnidirectional product, a plaque diffuser that is actually a very decent selection and very uniform in the ceiling plane. To get the best mixing and to get the best performance in a room, you want to involve as much of the ceiling as possible so that you're fully mixing the zone. Now, as throw is a problem, we also have acoustical issues, but we also have architectural issues. The image shown on the left is for a conference room in an architect's office in the west coast of the United States. Now, the diffusers along the side are actually one-way active chill beams. The light in the middle of that cloud is suspended on cables, and as much as we normally worry about performance for the human occupant, we also have to concern ourselves will the light sway in the wind and cause occupant complaint because of the change in lighting. So this was a physical mock-up that was tested to make sure the light didn't move. On the right is a university in the southeast United States where they renovated an existing structure, and these are active chill beams installed. Now, a slight difference, I believe, in how active beams are applied in Europe versus US is that ours are not always constant volume. We do variable air volume here more, and as a result, we have to concern ourselves no ceiling at low volumes where the air come down and hit an occupant in the head. So that was also a consideration. To do this comfort estimation, we normally rely on ASHRAE Standard 55, which is the thermal environmental conditions for human occupancy, where we will go in and measure at the ankle, the seated head height, the standing head height, the velocities and temperatures, and estimate the draft rate ratio and make sure that we have less than 20% complaint rate. Now, to do this, we use omnidirectional hot wire anemometers and temperature sensors. And we can also estimate to the European standards, but not with this velocity sensor. It's not fast enough to do the turbulence intensity. To give you a sample of natural ventilation testing, oops, I have 4 images. This is a hybrid room where we have natural ventilation coming in this test chamber. We have a glazing wall that's either hot or cold, and we have a convective or radiant cooling panel at the top. These are called a sail. And as you can see in the top image, the chilled ceiling is about 16.3 degrees mean water temperature. We've measured in the room the operative temperature, which is a combination of velocity and radiant, as this has a strong radiant potential, and we're at 26.8 C. well within range, and we have room loads simulated inside the space for a typical office. Now, theatrical smoke was applied to the ceiling here in an effort to see how far the warm stratified air would travel across the ceiling, and you can see here it didn't make it very far. It hit these convective radiant cooling panels and immediately fell down toward an occupant. So the whole goal is to make sure that heart velocities are not too high to cause draft rate. Now, as we start changing the parameters with natural ventilation coming through, a 24C entering air temperature, 200 liters per second, we see actually because of the motion of the air through the building space due to stratification, we see a breakup length of 2.5 meters of penetration, which then puts it directly over the occupants, which is actually part of our goal. Now, when we have the full load scenario in the building with a warm glazing wall, the breakup length is shortened, and as you can see in the other case, with a much entering air, much higher rate, the breakup length is about the same. Now, this is a fraction of all the tests that run in this particular scenario. We definitely don't have time for that. But to just give you a feel for some of the characteristics that we can look for and test and actually often have to do for those unusual situations. These mock-ups, they actually help us verify system performance. We have a lot of data in our industry that we can use to predict the performance of a building, but when you start doing unusual things, and as our loading characteristics change, our lighting loads are now LEDs a lot, we have less heat-intense computers, we may have higher density occupancies. These things are all dynamic, and so whenever we do anything a little unusual, or we're trying to discuss with a designer the possibility of doing a new type of distribution to save energy, which is always a good goal, we often rely on a mock-up. So what you see on the right-hand side is a mock-up. I know it doesn't look like it, but it's of a patient room. You have heat loads, displacement ventilation. The lower image is actually the CFD verification of that. And we like to do both because if you have a physical test and you validate it with a computer, then you know as you go through the rest of the building spaces, your model is most likely fairly accurate. And we've done this for classrooms. The church retrofit is the last thing I'll talk about here. This was the first cathedral built in the United States. Doesn't look like it, perhaps, but it was a naturally ventilated building. In the 1960s, they put in forced air systems, and as the priest described it, it became a walk-in freezer. So that was definitely not the goal, although the site it's located in is very hot and humid in the summer, so I guess a walk-in freezer is better than hot and humid. In the early 2000s, the architect came to me and asked if we could convert this back to a stratified system but use conditioned air, and so we used displacement ventilation in this. Now, there's a lot of things I could talk about this, but due to structural interference with the old structure not designed for duct, we had to come up with a way to make it happen. We set up this mock-up. Those are some of the most uncomfortable kneelers you'll ever be on, but we had the architect, the engineer, myself, and several volunteers on them trying to see if we would cause our feet to be too cold. So as bizarre as that sounds, that was a great success and just gives you a bit of a feel for what you could see in a testing scenario. Thanks.
Thanks, Jerry. The mental image of you kneeling on those kneelers will live with me for quite a while, I think. I think we're going to move swiftly on to Dave Clark. His presentation up. Dave is the Technical Director of SRL Technical Services Limited, which he joined in 1989 as a trainee acoustic consultant. He's progressed through the ranks from senior account acoustic consultant and office manager to joining the board in 2001. Despite managerial and directorial responsibilities, David has remained continuously involved in acoustic consultancy for the last 26 years, working on projects such as Crossrail and Dubai Opera House. David. David, are you with us? Roy, are you around? Are you with us?
Oh, here, yeah.
Roy, I'm going to, if you don't mind, I know you're always up for a challenge.
Cool.
I'm going to hand straight over to you. I'll introduce everybody to you first, though. Let me just get this slice up here. Roy Jones is the technical director, no relation of mine, I hasten to add, of Gilbert's Intellectual Limited, where he has worked for 28 years. Along with the CIBSE Natural Ventilation Committee, he's a member of the CIBSE Guide B Update. He's also acted BSI on ventilation of buildings, heating and hot water services and fire resistance tests. And he's also on committees representing HEMAC and Trade Association, the Building Engineering Services and the wider construction industry. Roy, over to you.
Thanks, Ben. I just can't see the PowerPoint at the moment. Can you put it up there for me?
Okay, so I will try to bring it back.
That's it, it's come back on.
Is that okay?
Yeah, I just need my slides up then, please. That's it? Okay, welcome everyone. This part of the webinar will explore the testing requirements from the manufacturer's viewpoint. Product testing by the manufacturer is vital, and for this presentation we'll look at the modulating damper only. Manufacturers need to be trusted and ensure their products are suitable and fit for purpose. That's true whatever's being manufactured. And the natural ventilation schemes, where products like these are used as part of the building facade, this is extremely important, as they actually form part of the building envelope. They must perform consistently to protect the internal spaces and ensure the correct environmental conditions. Okay, so everyone wants a quality product. Sorry, Benson, has gone on the slides, 2 seconds. That's it. Hold there. Apologies for that. So everyone wants quality products, whatever they buy. Natural ventilation obviously is no different. Manufacturers need to provide evidence of testing to provide confidence to the industry. As a proud manufacturer, we strive to meet any and all required standards. We in particular take testing extremely seriously as part of the development and manufacturing processes. We have our own environmental test facility and research and development departments which are tasked to follow standards and come up with test methods to provide assurance our goods are capable, resilient and suitable for the proposed use. Okay. So, sorry, it's just skipped on again, 2 seconds. Okay, so the damper's in the spotlight. Concentrate on this single product. The main function of the damper will normally form part of the building. It will be utilised as both internal and an external component, therefore has to be designed to suit both situations. The damper is also used for both inlet of the air into the building and for exhaust ventilation, so must perform both of those functions adequately. Therefore, stringent testing is required to ensure that it meets its required performance. So, there are 3 main characteristics that we're going to look at here, and they're going to be focused upon for reviewing the damper testing of this specific product. The damper, therefore, needs to be operationally correct as a dynamic device, thermally sound, and correctly sealed. Other tests for noise, weathering, flow rates, etc. have generally been ignored for the moment, but obviously are still key to full product compliance. So, operational. We need to test the product works. Simple as that. To do this, what we've done is we'll open and close the damper many thousands of times before releasing into manufacture, when finalising the final damper design. This will ensure the product meets the required standard of performance and simulates a lifetime test. Conducting these tests and providing test data shows that the unit won't simply fall apart or fail after a short number of operations. What we do to achieve this is connect the damper to a fast running motor. We then set the motor to run open and closed to produce full cycles. We have no specific standard to follow, but have produced a method for the damper to produce and provide a robustly tested product. We therefore gain many years of operation within a few weeks of testing. Using a calculation of 5 full open and close operations per day, we strive to pass the lifetime of the building and typically aim for at least 50 years of service. Okay, so the product also has to be thermally sound. This will protect the building and form part of the seal to the structure. To that end, we test the product for its calculated U value and provide that information. EN 1751 provides specific testing details to allow a U value to be calculated. As can be seen, we use a calorimeter and mount a 1 meter by 1 meter damper attached to the rig itself. The box is then pressurized to a 50 pascals level, and then the temperature elevated 30 degrees above the room temperature. The temperature difference from the rig to the room are then measured and calculated, and this then provides the thermal transference U value figure. So the damper needs to be correctly sealed. The damper, when closed, obviously. Tests are conducted on the building to prove the building as a whole meets Part L of the building regulations. That test pressurizes the building to 50 pascals to meet the notional building leakage, typically less than 5 meters cubed per hour per meter squared, or even lower if specific designs require a tighter building seal. The damper is therefore tested to ensure it meets the design requirements also. To be able to prove this, our dampers are put through their paces as they come off the production line. All dampers are tested this way, with results recorded and logged to provide traceability. Here we're demonstrating how we provide the test. After initial operation and function testing to ensure the product operates correctly, we move the damper to the rig and place in position. The rig we manufacture in-house using our own tool room and adding an accurate measuring device for pressure and leakage to be recorded. We then seal the unit onto the rig as would be fitted on site. We attain the seal, which is obviously vital for use in practice as well. The rig can take any single damper size, and the fixing clamps are movable, as the dampers are produced in millimeter increments. Once correctly fitted to the rig, pressure is applied at a rate of 50 pascals across the whole of the rear of the damper. Just to stress the fact we undertake this on every damper to ensure that they're compliant as they leave the factory. This also gives us a quality check, so we know they've been correctly manufactured. From the test, we receive a leakage rate for each damper. As can be seen, we have a matrix and spreadsheet to calculate the allowable leakage for each damper type and size. This is then recorded on the product and on a test document and signed off by the operator for full traceability. These are the types of tests we perform to ensure that as a reputable manufacturer, we provide a product both ourselves and our customers are certain are fit for purpose. Testing is vital to keep the high standards for the natural ventilation industry. This will help keep natural ventilation a primary thought when designing a ventilating system for a building. We as manufacturers must take testing seriously, provide confidence to the industry that we have tested products to meet the required demands. And that's me. Thanks for listening.
Thank you, Roy. I hope that Dave Clark is back with us. Dave, are you there? Let me know if you can hear us. In the meantime,
can you hear me?
Fantastic, great. Yes, loud and clear. Well, over to you.
Okay, well, thank you very much for listening. Irony that the acoustic consultant can't be heard. Anyway, I'm going to talk a little bit about the ventilation noise side and the relevant testing involved with this. Hopefully, we can move on to the next slide. Thank you very much. So, why do we care about noise? Well, there are important things. It's annoying if it's too loud, if it sounds unpleasant, but also it can be annoying if it's too quiet, as sound actually, ventilation noise particularly, can then mask unwanted sounds. Criteria therefore needs to be sensible, and on that basis it mustn't be too high but not too low. And just one little point that is crucial is that it's best to consider noise at the outset, because that will give you the optimum solution and for the cheapest, which is what we all want.
Dave, can I just interrupt quickly? Any chance you can get a bit closer to the mic for us? I think some of our listeners are struggling to.
Yeah, okay, does that sound better?
Beautiful, that's much better, yeah.
Okie dokie. And am I operating the slides or are you?
If you can do it, please do it.
Right, hopefully I am. So, where to start? Basically, acoustics is a complex subject, as I think has been alluded to earlier, but in the famous words of Stephen Covey, you should begin with the end in mind, and the end is the noise criterion. So, here is a schematic of a room where you have an open window where noise and fresh air, hopefully, is coming in. Noise, not so hopefully. You also have a fan, which helps extract it, but unfortunately that creates noise as well. And you probably have a noise criterion in the room, which might be set as an NR level or a dBA level. Now, NR is for noise rating level, not noise reduction. We do like to make things complicated in acoustics, so NR in this context is noise rating level. And it's a set of noise limits at different frequencies, all in terms of decibels. Now, I'll try and very briefly explain what a decibel is. Basically, a decibel is a ratio of noise levels. So it's one noise in relation to another. And this also makes noise complicated, because we can talk about silencers or attenuators having acoustic attenuation, and we say that's in decibels. We also talk about noise levels, apparently objective noise levels, absolute noise levels, being in terms of decibels. And what really we're talking about in the latter is that if we're saying it's 35 decibels loud, it's really 35 decibels louder than the threshold of hearing. So everything is referenced to something else as decibels, and in terms of noise levels, it's always referenced to threshold of hearing. So you can actually get negative decibel levels if you want to go quieter than that, but we consider 0 decibels as the threshold of hearing. So in this situation, what we're trying to do is we need to know how noisy it will be. And obviously on this slide, you've got two sources of noise. You've got the noise coming in through the window, and you've got the noise from the fan in the ceiling. Now, the good news with a mixed mode unit is that you can actually have the window a bit more closed and still get the same amount of air in. So that means the noise coming from outside is quieter. However, you have added another noise source, which is the fan. So it swings and roundabouts here. So what are we trying to achieve? Well, what we're really trying to do is we want to know how noisy it is in the room. So if we have a noise source, S, we can calculate how loud it is at listener L by knowing how much sound travels directly, the big thick red line from S to L, but also you've got all the reflections off all the walls, which will depend on what the walls are made of. So sound is a bit like heat, and sound pressure level is what you hear, but as you can see from the previous slide, it is highly dependent on the acoustic environment. If you have a room with lots of hard surfaces, the noise will bounce around more and sound louder. If you have a lot of soft surfaces, soft furnishings, that will absorb a lot of sound, and so the same source will sound quieter. As I said, it's a bit like heat, so the relationship between sound pressure and the energy of that source is similar to temperature, heat energy. Temperature is what you feel, just as sound pressure level is what you hear, but the radiated power from the heater is akin to the sound power level, as we call it, of the noise source. Now, the key thing about that is that the heater will generate or give off the same amount of energy wherever you put it, just in the same way as the ventilation drill in this instance will give off the same amount of sound power, sound energy, wherever you put it. Now, we all know that if you're in a large room with concrete walls and floor, then and you put a little heater in the corner, it will still be quite cold. If you have a small bedroom with lots of soft furnishings, that same heater will feel warmer. And the same is exactly true for sound, that you can put a sound source in a very large room with lots of absorption on the walls, and it will be very quiet. You could have a very small room with hard surfaces, and the same source will be very loud. So we need a way of establishing what the noise of a fan or a part of the ventilation system is, regardless of all these other factors. And so we define sound power level because that then gives us a definitive number which the unit has regardless of wherever you put it. And you can test that in an acoustic laboratory, or you can test it in field. So, for example, it's very common to go to a factory to measure how noisy an air handling unit is, or a fan. But the point is, you don't really measure sound power level. It's an intrinsic thing, that it's a property of it, but you actually measure the sound pressure level and calculate back. I won't go into the great details of that, but basically sound power is defined as the sound pressure level. The sound pressure level is the sound power square meter. That's the wrong way around. So when you measure the sound pressure level, you can work out how much sound power is coming from it. The BSCN ISO 374X series gives measurement methods. So you can 3741 gives you a method of measuring inside a laboratory, and that's a precision method. 3744 and 3747 give engineering or survey methods for factory or outside, literally in the field. You could measure on a large concrete area. We do actually measure some pieces of equipment out on airfields because they're great. The key thing when you're measuring or trying to measure the sound power is you want to remove interference, firstly from other noise sources. So there's no point in trying to measure something you can't hear it because you're right next to a busy road. But the second thing is you're trying to remove the effects of the acoustic environment. So if there are any reflected sounds, obviously you're measuring louder than you would be. So it's trying to make sure that you eliminate all that so you get a clean measurement of the sound power. So, I can't move to my next slide for some reason. There. Can someone help me?
Is it now showing the right slide, Dave? David, we lost you. Yes, unfortunately Dave's got a fly. I think if we can get him back, we'll get him to finish his presentation. It was only a couple of slides from the end. But we've had a few questions through from panelists, and the first one is directed to Mark Roper. Hi, Dave, are you back?
Yep, sorry about that. That's right. my situation. Shall I go back and finish my talk?
Yeah, you go to wherever you would like to go. Is that, are you on the right slide?
I'll just have to go back and check. Sorry about that. Apologies.
No problem. No problem. If you use the up arrow or the down arrow,
okay. Yeah, fine. So I'll just run through this. Basically, as I mentioned earlier, sound power level is an intrinsic property of the fan or the noise-making thing, and under normal atmospheric conditions, it's effectively independent of where the source is located, which is ideal because it's then a great starting point. You know where you're always starting from, and you can calculate the sound pressure level, which is what you actually hear, once you know the sound power level plus distance, how far you are away from that source, the acoustic environment you're you're in, whether you're sort of in a free field environment, which is outdoors, or you're in a reverberant field, which is indoors. If there's any obstacles in the way, a wall, a ceiling, any ductwork, or attenuators, acoustic screening, and the existing ambience, i.e. other noise that is present. So in order to predict the result, first of all, you start with your fan sound power level and you deduct any system losses. You can then calculate the noise level of the listener, both in terms of the direct field and the reverberant field, i.e. the reflections off all the walls and ceiling. You add that to any external noise break-in, and you see if it meets the criteria. If it does, then great, happy days. If it doesn't, then you probably need to add more attenuation or get a quieter unit. For example, a common way, if you have fan coil units, which are notoriously noisy in systems, one of the ways to do it is to get a bigger unit and run it at lower speed, and that gives you lower noise. But the point being is that if you go through this system and you measure, the way you normally do this is you will firstly measure the noise with the fan switched off and the window shut to see what the true background is. You'll then open the window, see how much noise is coming from outside, and finally you'll switch the fan on. And by going through that process, you can identify, if you are exceeding the criteria, you can identify where the problem is, and therefore what to do about it. Is it actually there's too much noise coming from outside, or is it your fan that's too noisy? So sorry about the technical glitch in there, but hopefully that was okay in the end.
Thanks very much, Dave. We're going to move straight on to some questions. We've had a few through. If panelists could be ready with their microphones. The first one is for Mark Roper, and this one comes from Hugh Poppy, who says that he was interested to see the Class A louver classification, which shows that even a Class A louver can pass 0.75 litres per hour. And he suggests that maybe as when a louver performance improves, should there not be a classification for higher performing louvers, for example, an A+ louver? Does that seem workable, Mark? I think you've muted, Mark.
Yes, sorry, I managed to turn on the webcam and switch off the microphone. Let's try that the other way around. Hello there. Right, it would be a possibility. It's already a fairly fine gradation already, so we're only talking about 1% of the water getting through, and we do list the performance in terms of a percentage. So if you have a 100% louver, and we do see them, not a huge number, but they are out there, then there is a numerical value in those results. So I guess it's whether increasingly fine gradations in the classification would help when there is already a numerical number if people are looking already for the very top end. So it would be a possibility, but perhaps I'm not sure of how great a benefit that would be. Possibly those who are listening to the webinar, if they think it would be of great benefit, perhaps should drop me a line and we can look at whether we should be trying to do that. But that would be my view on that one.
Okay.
Okay, we have another. Sean, we have another question on acoustics for Dave Clark. So Dave, thank you very much for your presentation. So the question is this. Suppliers who therefore just simply quote a measured sound pressure level in one instance and say that therefore demonstrates compliance with their equipment, are we correct that actually surely all suppliers must supply sound power levels of their given units if they're noise generating? And if not, should we assume that they're hiding something?
Not necessarily. If you can get sound power levels, that's perfect, because that is, as I said, that's an intrinsic property. It's all on the same playing field, which is what we want from tests, so we can compare like with like. There are basically two other types of measurements that are valid. One is if they have measured a unit and it's in a free field environment outside, and they can say, well, we measured this at 1 meter away, or 3 meters away, or 10 meters away, then we can actually work the sound power back. That's dead easy. Effectively, what they've done is followed one of the British standards, the BSRIA and ISO standards, in terms of they've done half of the work by measuring the sound power level. So that's, again, absolutely fine. If they don't say, if they just say it's a sound pressure level and won't give you any information at all about how it was measured, then you can do nothing with it. A very common way, grills are often specified in terms of an NR rating, but actually what it is it's a sound pressure level based on the sound power level and the room, effectively a room absorption coefficient of -8 decibels. So if, for example, they're saying it meets NR 35, what that really means is that the sound power level of that grill is NR 43, i.e. 35 plus 8. If your room is a small room and is quite live, your room correction might be nothing at all. It might even be +1 or +2. So you cannot say, well, just because I've got a noise rating of a grill, which says it's going to be 35, but it actually is 35 in situ. As I said earlier, it's absolutely crucial that you know the environment in terms of where it's measured and also where you're putting it.
Okay, so that's very helpful. So sound pressure on its own is actually not very helpful unless you know something more, a lot more about the environment and where the measurements were taken from. Great. Correct. Over to you, Ben.
Thanks. I've got one final question before we wrap up. I was impressed by the testing that Roy and Jerry both presented to us, and one thing that struck me really was just how much these things must cost. And so my question to Jerry is, what circumstances do you consider creating a mock-up? And to Roy, have your quite extensive tests paid back quickly? So Jerry first.
That's a common question, actually. Anytime we haven't looked at a combination of equipment such as the sales and stratified systems, and the information is not present in literature, which is unfortunately very common since we're adding new energy saving systems all the time. Those are the things that usually indicate that we need a mock-up. Or perhaps it's related to the end client. I have had situations where we're retrofitting buildings. You know, very common, 80% of the building stock I deal with actually already exists, and they're putting new systems in. Anytime that we have an area of concern such as an orchestra choir area, a performance center, those often are very commonly requested for mock-ups. And also places that see changing technologies like hospitals where we have an increase in the energy density inside a patient room due to the equipment. Those are often also mocked up. But the truth is, do they pay back? I believe they do pay back. They pay back every time, if only because we have information then that can be used for the next design.
Yeah, that makes sense. Roy, can you add anything to that, please?
Yeah, basically I think you're saying they cost a fortune, which is probably quite correct. But what we have to do at the start of any R&D process is justify what we're going to do to the product, including testing. We all that when we start designing the product. So therefore, that's costed into the whole program, and therefore we'll look to see what the kind of payback period is on that before we press the button and decide to manufacture a certain style or type of product, including the thousands of pounds for extra rigs and things like that we provide. As well as the ability to use our own environmental test chain.
If I might address that last one, because I failed to mention this. I have had projects that have no payback, and they're clearly identified during the mock-up, and therefore the design was changed. But I have had buildings that have a 3-year payback in energy savings. Oftentimes, our primary concern is the energy efficiency in addition to the thermal comfort. And depending upon how you bid it and the complexity, the cost can be very expensive to your point, but typically nominal.
Wonderful. Many thanks to everybody who's joined us today. In particular, many thanks to our panelists. I hope you've learned a thing or two, and we can see that hopefully testing pays and how it's worth creating a culture of testing within your own businesses. There will be a recording of this webinar, and that will be placed on the Natural Ventilation Group's website. That's at allthews.cibse.org/NVG. Please visit it in the near future to listen again. I'd like to thank my co-host here, Sean Fitzgerald, to my employers, University of Nottingham, staff here, in particular our IT support who got us up and running earlier, to Remy Carrier and Mike Barker and Nari Hughes, who helped with marketing, but in particular to Richard Howard, who's worked in the background, keeping quiet, and without him, none of this would have got off the ground. So thank you all to everybody, and we hope you'll join us again. Bye-bye.